Welcome back, Algebra 2. We're going to be taking a look at the periods of the trig functions. Let's start by drawing a unit circle, which, if you remember, is just a circle of radius 1. And we're going to look at the angle pi over 6 radians, which, if we draw in standard position, would be this angle here. And if you want to look at the corresponding point for this angle, it would be square root of 3 over 2, comma 1/2. And if you're wondering where I got that from, I know that this is just a 30, 60, 90 triangle that we're looking at right here, right? And I can label the sides whatever I want, as long as they have this 1 to 2 to root 3 ratio. And if I find cosine of pi over 6, which is just cosine of 30 degrees, that would be adjacent of our hypotenuse. And then sine of pi over 6 would be opposite of our hypotenuse. And if you remember from the previous discussion, when we look at the unit circle and we look at the point that corresponds to the unit circle, the x-coordinate will always be cosine of that angle, and the y-coordinate will be sine of that angle. Now let's look at the angle pi over 6 again, and think about what would happen if I were to add 2 pi to that. Right, here's pi over 6, and if I were to go 2 pi more, I would end up with the same terminal side. So because by adding 2 pi and I end up with the same terminal side, do you see how the cosine and sine of this angle will correspond to the same values as the cosine and sine of pi over 6? So cosine of pi over 6 plus 2 pi will still equal square root of 3 over 2. Because they share the same point. And sine of pi over 6 plus 2 pi will equal 1/2. Right, so again, I hope you can see that by adding 2 pi or even subtracting 2 pi, the point on the unit circle that corresponds to that angle is still the same. So that means that the values of the trig functions will be equal to the corresponding trig functions of theta, which in this case is pi over 6. So to generalize this, if I want to find sine of some angle plus some multiple of 2 pi, this is simply equal to sine of the angle itself. And if I find cosine of an angle plus some multiple of 2 pi, this is going to just simply equal cosine of theta. And if you remember, we had our discussion on coterminal angles, right? Which are angles that have the same terminal side. And we talked about how trig values at coterminal angles are the same. And so this falls in line to what we said with coterminal angles. And so functions that exhibit this kind of behavior are called periodic functions. Let's define what a periodic function is. So a function f is called periodic if there is a positive number p such that f of theta plus p equals f of p. So we're going to use this idea, but where f is going to be our trig functions. Now the smallest such number p, if it exists, right, is what we call the fundamental period. But we'll just call it the period of f. And so when we look at the sine and cosine functions, the period for those two functions will be 2 pi. And because sine and cosine have a period of 2 pi, it readily follows that cosecant and secant will also have a period of 2 pi, because cosecant is a reciprocal of sine and secant is a reciprocal of cosine. And so the values of sine and cosine will pretty much correspond with the values of cosecant and secant, right? And so they will also repeat every 2 pi. Now, for tangent and cotangent, on the other hand, they will have a period of pi. And so just be very careful with this one, because you don't want to bunch up tangent and cotangent with the other 4, right? The other 4 all have a period of 2 pi. Tangent and cotangent will have a period of pi. And so these are what we call our periodic properties, where if I have sine of theta plus 2 pi, I know that's really the same thing as just sine of theta. Cosecant of theta plus 2 pi would just simply be cosecant of theta. cosine of theta plus 2 pi would just be cosine of theta. And again, the first four are true because the period is 2 pi. Now for tangent and cotangent, if you notice here, they have a pi instead. And so here we'll get tangent of theta, and here we'll get cotangent of theta. So here we have cosine of 570 degrees. And because cosine has a period of 2 pi radians, or 360 degrees, I can write this as cosine of 210 degrees plus 360 degrees. Because again, this is just the same thing as 2 pi radians, right? And so according to our periodic properties, I know that this is really just equal to cosine of 210 degrees. So if you don't have these values memorized, what you can always do is first draw this angle in standard position, which will look something like this, right? And if you look at the triangle here that's formed, right, using the fact that my reference angle is just 30 degrees, we end up with a 30, 60, 90 triangle, where I can call this side here 1, the hypotenuse is 2, and the longer leg is always square root of 3. And so here I know that in quadrant 3, cosine will be negative. And the reason why I remember that is because, well, you can always think of it this way, ASTC, right? In quadrant 3, tangent is only a positive 1, so I know cosine is negative. But you can also just use the fact that if you imagine a unit circle, any point in quadrant 3 has an x-coordinate that's negative, and we know that the x-coordinate corresponds with the cosine values, right? And so we can use that fact as well to say that cosine of 210 has to be negative. And then from there, looking at your triangle, cosine, think adjacent over hypotenuse. Using our reference angle right here, right? The adjacent would be square root of 3, and the hypotenuse is 2. And so you get negative square root of 3 over 2. Let's look at another example. Here we have cotangent of 5 pi over 3. Now cotangent has a period of pi, so I can rewrite this as cotangent of 2 pi over 3 plus pi. And I know that this is just simply cotangent of 2 pi over 3. And then from there we can draw this angle in standard position. So 2 pi over 3 would be less than pi. This would be 2 pi over 3. But we want to look at the triangle formed here, where one of the legs is always on the x-axis. Because this angle right here, right, this is our reference angle, which is going to be just pi over 3, which is the same thing as 60 degrees. So we have a 30, 60, 90 triangle. All right, let me put this 30 here. So labeling the sides, I know that this is a 1. The shorter side is always 1. The hypotenuse is 2. The longer leg is square root of 3. In quadrant 2, cotangent would be negative, because again, we know that sine is the only one that's positive in quadrant 2. And then cotangent is adjacent over opposite, right, the reciprocal of tangent. And that will give me adjacent over opposite. And if I simplify that, I get negative square root of 3 over 3. Okay? So again, you can always draw right triangles and use the reference angles along with the signs of the trig functions. And here we're also using the fact that the period of cotangent is pi. So every pi it repeats. So cotangent of 5 pi over 3 will really be the same thing as cotangent of 2 pi over 3. All right, at this point, I want you guys to pause the video when work it out, and when you're ready, press play. So here we have sine of 9 pi over 4. Now we know sine has a period of 2 pi. So I can write this as sine of 2 pi plus pi over 4. And this is the same thing as sine of pi over 4. Once again, if you don't have this memorized, you can always draw pi over 4 is a 45-degree angle, right? You can always draw a 45, 45, 90 triangle. Label the sides 1, 1, hypotenuse root 2. And if you do sine of pi over 4, you can use a reference angle. We know in quadrant 1, sine's positive, and then sine will be opposite of adjacent, which is 1 over square root of 2. And if you rationalize it, you get square root of 2 over 2. Hopefully you got that right. If not, learn from your mistakes. So we're going to look at one more example, number 4 right here. As usual, when your video says your turn, press pause, work it out, and then press play. So here, I'm going to use the fact that secant has period of 2 pi. So I can write this as 2 pi plus Now 2 pi, by the way, is just 12 pi over 6. And so I'm left with 11 pi over 6. And so according to my period properties, this is just secant of 11 pi over 6. So at this point, you can always just draw a right triangle. But first, you want to draw the angle in standard position. So 11 pi over 6 would look something like this. Right? But again, you want to be looking at the reference angle. The reference angle would be just pi over 6. Pi over 6, by the way, is just 30 degrees. So this is a 30, 60, 90 triangle. So I'm going to label the shortest leg 1, the hypotenuse 2, and the longer leg square root of 3. And so from here, using this reference angle right here, I'm going to find secant of that angle. So in quadrant 4, I know secant is positive because cosine is positive. And I know secant is the reciprocal of cosine. So if cosine is adjacent over hypotenuse, I know secant is hypotenuse over adjacent. And so the hypotenuse here is 2. The adjacent is square root of 3. And then if you rationalize this, you get 2 square root of 3 over 3. Right, so we're pretty much just applying all the stuff we learned before when it came to reference angles and positives and negatives, right, depending on what quadrant the angle is in. And so we're pretty much just combining all that together to evaluate trig functions. And now we're throwing in the fact that these trig functions have periods. And so we can use these period values to make these angles essentially smaller, right? Because we know they have the same values in the end. So guys, make sure you understand this concept of what it means for these functions to be periodic and what the period of each of these functions are. Because when we graph these in 6.6, these ideas will come up again, okay? So just kind of keep that in mind. Anyways, guys, review your material before you move on to the next video lesson.